Okay, good afternoon. So there is a short lesson. If you remember, some of these exercises was left without solution before, so I will solve them and then I give you time to practice on your own. Okay, so let me just review a little bit. So the point is we learned about concavity of functions. Is it working? Okay. We learned about concavity of functions, so we learned that if the second derivative at the point is positive, the function is concave upwards at that point, and if the second derivative is negative, then this is concave downward at that point. And then we also learned how to find the inflection point of a function. And what was the recipe? If you remember, let me just review it shortly. So the inflection point has something to do with the second derivative. Of course, if you want to determine the second derivative, it is completely natural to start with the first derivative. So if I want to write a recipe for determining the inflection point, this is the recipe. The first step that you do is actually to determine f prime. After that, you determine f double prime. But then you put f double prime equal to 0 and start solving this equation. This will give the possible candidates, so I have written them in italics, so that understanding that these are just only candidates. So let us assume that x equals to a is one of the solutions here. You cannot immediately jump and draw the conclusion that, oh, I found the inflection point and x equals to a is the x-coordinate of the inflection point, because it might be a fake one. How we should understand that? We need to set up a table like this. It is very similar to the table that you had, which we called the sine table for the derivative. The only difference is that the middle row, instead of being information about f prime, it's the information about f double prime. But it really looks the same. And then you take this number that you found and put it in the x row. And then, of course, the second derivative at that point becomes 0. And if you put this in the function itself, it becomes f of a. Then you determine the sign, positiveness or negativeness of f double prime on the left side of a and on the right side of a, exactly with the similar method that you learned by plugging some random number before that. I told you again, this only works if the second derivative is continuous, and that is the only functions that you deal with this in this course. So this method always works. Okay, so assume that on the left you realize the second derivative is negative. It means that your function on this interval is concave down. And it is positive on the right side. It means that suddenly it becomes concave up. So in that case, f a is really an inflection point. Yes? The other way around also means that a and f of a is an inflection point if previous to the point a, it is concave up, and then suddenly after that point it becomes concave down. So in the case 1 and 2, this candidate is a real inflection point, but it might happen that no, you face this situation that the left is concave up, the right is also concave up, and then this means that no, even though you found this as a candidate, but that candidate does not work, and a or f of a in this case is not an inflection point. The same explanations for the last item. So there are 4 possibilities. If this or that happens, that candidate is a real inflection point. In the other 2 scenarios, it is not an inflection point. So that is the recipe that you need to know. It's very simple, by the way. And if I remember correctly, last time from this example 3, we solved number 1 and 2. I will solve 3 and 4 today with your help. And there is also another problem. These kinds of problems, they are considered level 3 problems in your book. Not because algebra is harder. By the way, the algebra here is much simpler, but might be it is conceptually a little bit harder, which I really don't understand that much. Anyway, so let us go back and solve these 3 problems, and then I will give you time to practice on your own. Okay, I would recommend you try to come with me, because if I explain everything on the board, of course, you will understand. The point is that you learn how to do without me. Okay, so let me write number 3. So f of x is equal to e to power 2x and minus 2x squared, and then I have plus x minus 1. So the question asks for finding the inflection points. It's always good to have GeoGebra available, so let me also open GeoGebra. Anyway, so let us start. I want to find inflection points of this given function. The recipe tells you that you need f double prime. For finding f double prime, of course, the first step is to find f prime. I hope that you haven't forgotten the formulas. If I want to write the derivative of that one, this is playing the role of the constant in your formula table. So this constant goes down. This is an exponential function, yes? And then the function repeats itself. And then differentiate this one, it becomes minus 4x. Differentiate this one, it becomes 1. Differentiate this one, it's 0. So that's my first derivative. The second derivative, I pretend that this is the given function. I do differentiation process. I apply differentiation process once more. So again, I have a 2 here. 2 comes down, so it becomes 4. But the function repeats itself. And the derivative of that one is simply minus 4. Okay? So now I need to find the candidates for the inflection point or points. So what I have to do, I have to myself equate the second derivative equal to 0 and solve the equation. So what should I do? So I would say that, okay, 4e to power 2x minus 4 is equal to 0. I move 4 to the other side. So 4e to power 2x becomes 4. And I divide everything by 4. So e to power 2x becomes 1. But hopefully you can immediately tell me what x is. X is 0, yes? Because that's the only answer that we have. E to power 0 is 1. Or if you want to, you can solve it using 2x is ln of 1. But you know that ln of 1 is 0. So 2x is 0, x is 0 as well. Okay, but it is better not to put it in the box, because when I put it in a box, you get the feeling that I have accepted that. This is just a candidate for the time being, okay? In order to understand that, I have to set up the table. The table consists of 3 rows. The first row is x, the second row is f double prime, and the last row is f. So the number, my candidate is 0. So you can assume that here is minus infinity up to infinity. Why? Because I do not have any limitations about the values that I can put into the function. The domain of the function is infinity, so this is why I do not put 0 here. I assume that here is minus infinity, here is positive infinity, so I put 0 somewhere here. Okay, this is clear that if I put 0 in the second derivative, it is clear that the answer is 0 because I myself put the second derivative equal to 0 and I got this answer. But it is not clear what f is. I have to take this number and put it in the original function. You see, this is the f row. So whatever you want to get here, you have to use the original function. So I take 0 with me and put it here. So what happens? E to power 0 is 1. This one and that one are cancelled. And when I put 0 here and there, that's also 0. So coincidentally, again, everything is 0. Yes? This is always 0, but there is no guarantee that these are 0. But everything in here coincidentally is 0. Okay, so then I need to decide the sign of the second derivative. Don't get confused. The second derivative is this expression. Yes? So you want to know if it is positive or if it is negative. So what you do, I don't care how you convince yourself. If it is correct, that's enough. But if you want to do a systematic way, because the second derivative is an exponential function, and exponential functions are always continuous, so if I pick a random point and I can determine the sign, it will work for every number in that interval. So let me choose a random number, for example, minus 1 on the left, and put minus 1 in the second derivative. You can do these things in a scratch paper. If I put minus 1 there, it becomes e to power minus 2 and then minus 4. Okay, is this number positive or negative? Let's assume that you don't have calculator available. So is it positive or negative? Yes, because for example, you can factor a 4 out. E to power minus 2 is 1 over e to power 2, and then what is left from here is 1. E, if you remember, it is around 2.7. If I square it, it becomes bigger. So anyway, 1 over e2 is definitely less than 1. So if I take 1 out of it, it becomes a negative number. If I multiply it by 4, it becomes negative. I don't really care about how you convince yourself correctly. If you just write the correct sign, that's it. So this becomes negative. And if I choose a random number after 0, say 1 again, say 1, I put 1 again in that function, it becomes 4e to power 2 minus 4. Definitely it is positive, yes? Okay, so here what you can say this one is concave down here on this interval, and immediately after I pass this point, it becomes concave up. So the point with coordinates 0 and 0, okay, that's exactly the origin, is the inflection point. So it is not the fake one. It is not a fake one, it is a real one. So that's an inflection point, yes? Is the inflection point. So I can call it I, okay? So it's a good idea to check the graph using GeoGebra to have a better picture. Okay, so I want to draw the graph. So y equals to e to power 2x. So let me use, where is the keyboard? Every time the GeoGebra starts playing with us, you know. So where is the keyboard here? Do you remember there was a virtual keyboard somewhere? Okay, I hope that it understands when I type E. Okay, so let us see. Yes, I think it understands that. The e to the power of 2x. Yes, that's correct. Okay, then a minus 2x squared. So, and then I come down plus x minus 1, plus x minus 1. So that is actually the graph of this function. And I hope that you feel that this 0, by looking at the graph, I want you to have this feeling that this point is really an inflection point, yes? And it is not a terrace point. Why this is not a terrace point? Yes?
The k value isn't 0.
Isn't 0, yes? But it is an inflection point. Do you agree with me? Because you see, before this point on the left, the concavity of this red curve is downwards, and then immediately after that, it becomes upward. And sometimes if you make it hard, you can go here and try to rescale them. So because when you press on this one and come here, this cursor changes form so that you can actually rescale it a little bit to understand the graph better. So I think now it becomes very clear that this one, and then you remember, let us just repeat that. So, okay, I think it cannot answer this one. If I remember from last session, it only calculates the inflection point of polynomials. Let me see. So inflection point, I don't think it accepts, because this is not a polynomial. Yes? Why this is not a polynomial? Yes? Yeah, it has an exponential term in it, e to power 2x. This part of it is polynomial. So I don't think it will accept this from us, but let us insist, yes? E to the power of 2x, and then I go down minus 2x to the power of 2, and then I go, so I don't know why it jumps there suddenly. Yeah, that's correct. And then plus x minus 1, am I right? No, it doesn't understand that. And the reason is clear, because according to the syntax, that inflection point is only for a polynomial, and as we understood, it is not a polynomial. Okay, but you can test it in a little bit different way. For example, as Buell mentioned, the k value is not 0. So what I do, I know that the inflection point, let me call it I, is what? I don't know, okay. I is equal to 0 and 0. So that is the blue dot that now you see here. And ask GeoGebra to draw the tangent line to the curve at that point. So what happens? The tangent passes through the curve. So let us see. So I go here and ask GeoGebra to draw the tangent line to this graph at that particular point. And you see that the behavior that you expect is clear here. Before that, the red curve is below the tangent. Then suddenly, after that point, the red curve is above the tangent. So that's exactly the meaning of concavity, down and up. Yes? So that's also another way to test. So we learned that this syntax of inflection point only works as it mentions that this is a polynomial. Anyway, I will solve one more problem here of this type. Let us go back. So the question is this one. X to the power. If you don't mind, let me wait for you to solve it and then we continue. I give you 5 minutes, exactly the same question. I want you to find if there is any inflection point for this function. Okay? I'll wait for you for 5 minutes. Okay, what is your opinion? Is there any inflection point for this function? Nothing? Okay, so that is good. Because I was doubting a little bit how careless I was, because I want to give you an example that you really have to do that, because many students think that, okay, when we take the second derivative and equate it to 0, it is already guaranteed to have the inflection point. Yes, most of the time might be in the book, yes, but I want you to see that's an exception. There are some exceptions, so this is not just a fantasy, yes? We have to do that. Okay, because in all these examples, these 3 first examples, what we got was actually right. So you might get this wrong impression that, okay, why we should even do that, because this is always working, yes? I hope that I could actually, so that's good that this example does not work. So, okay, so now let me just solve the problem. What is that? F of x is equal to x to the power of 4 plus 2x minus 1. Okay, so why it's not working? So let us see. F prime of x is equal to 4x cubed plus 2. Okay, and then f double prime of x is what? 12x squared. Okay, so yes, you are right, it does not work. So f double prime, I put it equal to 0. Then what happens? 12x squared becomes 0. And then, of course, there is only one candidate again. That is 0. So you see, it is very similar to the previous problem so far. But then, if you are in a hurry and consider this as an inflection one, it is not correct, because if you just draw that, you realize it is a fake one, yes? So I have x, I have f double prime, and I have f. So x is this number. Of course, I put this back. When I put this back, I get minus 1 this time. Okay, but now I need to determine the signs, yes? On the left-hand side, I choose the random number minus 1 and put it in the second derivative. But because of this even power, I get a positive number. So this is positive. And then I go to the right, pick a random number, say 1, and I put it there. Again, I get a positive number. So it means that on the left and on the right, it doesn't matter on which side I am, this concavity is upward. So the concavity is not changed in the passage of this point. So this is a fake one. So there is no inflection point for this function. So I would say that no inflection points. So that is important. So this example shows that this part is indeed necessary. Okay, so that's also a good idea to draw the graph using GeoGebra to see what is going on, that this is a fake one. So if I get rid of these, okay, now let me type that function, y is equal to x to the power of 4 and plus 2x minus 1. And that is what you get. It's a little bit tilted, but I hope that you agree that there are no inflection points. Yes, let us see, by the way. It might not be clear what that point is. What we got on the board, it was 0 and minus 1. So that is exactly this point. And you see this is not an inflection point. So again, if you don't see it very well, go to this move graphic views and then try rescale them so that you can see. Yes. I hope that you see that no, this point that I found using calculation is not inflection point, yes? Because before that, the concavity is up. After that, the concavity is still upward. How can I confirm that graphically? How can I do that? I can probably go here, choose a point exactly here. Is that right? Yes, it is 0 and -1. Then ask GeoGebra to draw the tangent line for me for this one and that curve. So you see, this is exactly what you see. If you don't, so don't think that this is a flat part. This is not flat. Our eyes cannot detect that. If you want to understand that, you can rescale it the other way around. Yes, so you can pull it up, or and then simultaneously. I don't know. It doesn't work. Yes, it's working because these numbers are getting smaller. Anyway, so you see that the curve all the time is above the tangent line. So it does not have the property of being an inflection point. By the way, that's also good because this is indeed a polynomial. Let me put this in GeoGebra to see if GeoGebra understands that there is no inflection point for this function. Because that's a polynomial, GeoGebra knows how to calculate inflection points for polynomials. X to the power of 4, and I go down, plus 2x, and then -1. Okay, and then when I press enter, okay, so there is no difference in the syntax. So it doesn't understand. So this doesn't understand. In the previous case, do you remember? It was again question mark. In that case, we really did, we had an inflection point, but GeoGebra was not able to answer. It returned a question mark to us. In this case, it does not have any inflection point, but it is still returning a question mark. It was better to say there are no inflection points or something like that. Anyway, so that's it. And then there is one example of the different nature. So some words are given in the problem, and then you're asked to do something with that problem. So let me just go here and see the problem. Consider this given function. Okay, that's a polynomial type function. Determine a and b such that -1 and 0 is this function's inflection point. Okay, so if you don't mind, let me also wait for you because that's the last example I want to solve today. So I will give you a little bit more time to think about it and solve it, and then I solve it, and then we are done. Okay, so could you solve the problem? Did you find a and b? No? But why not? So it might be that the book is right that this is a higher level question, but this is not hard, yes? So let me first, this is important. If double prime of A is equal to 0, then, so let me write like this. I, A, and f of A is an inflection point. Okay. And once more, I, A, and f of A is an inflection point then f double prime of A is 0. So which of these statements, if any, is true from what you learned so far? Yes, I think, so two statements. I tell you f double prime of A is 0. I want you to buy this argument from me. Because of that, this I with x coordinate A, and of course f of A, is an inflection point. Or I with these coordinates is an inflection point. I can conclude that f double prime at this point A is 0. Is one of them or both of them or none of them is true? You want to say something, Sergey?
I think the second one is true and the first one is false.
the first one is false. We just saw it, yes? If the second derivative is 0, there is still a chance that this point is not an inflection point. That's exactly still on the board, yes? F double prime, when x is equal to 0 is indeed 0. But we realize that is not true. So this is definitely false. By the way, in mathematics, when we say a statement is false, it means that this is not the case that I can rely on it 100%. It might be you can cook up examples that this is right. And the first 3 examples were of that type. Yes? But when I say this statement is false, it means this is not the case that it is working 100% all the time. And it means that we cannot rely on it because we don't know. Is it the situation that this is not going to work, or is it the situation it's going to work? Anyway, this implication is false. But Sergey told this is true. I would say yes, that is correct, but at the level of your book. Okay? Because there is also a slight chance that this is not either true, because it might happen that the second derivative is not defined there. Yes? Now, because we might have this scenario. Yes? So if I ask you, is this an inflection point, you will probably agree with me that yes, this is indeed an inflection point. But if you remember, this is one of those points that the function is not differentiable because I have a vertical tangent. So it means that if you ask me what is f prime of a, if this point is a, yes, I would say that f prime of a does not exist. Of course, if f prime of a does not exist, f double prime of a does not exist either. Yes? So this is why we can say that this might be also wrong. Yes? And then, by the way, a very famous counterexample is the third root of x. So if you draw the graph of this function, it is like this. And I agree, I hope you agree with me by any definition, this is an inflection point. But if I ask you what is the second derivative of this function at 0, it is not defined. We can confirm that, by the way. It is at the level of your book. If I give you y equals the third root of x and I ask you to find out y double prime, the first thing that you do is to write this, and then you do it once, 1 over 3 goes down, and 1 over 3 minus 1 becomes minus 2 over 3, and I can do it once more. Minus 2/3 goes down, it becomes minus 2, 3 times 3 is 9, x to the power of minus 5 over 3. And if I want to write it a little bit simpler, I put minus 2 in the numerator, I put 9 in the denominator, I bring it with me to the denominator and make it positive. Now look, if I ask you what is f double prime at 0, it is not defined because you cannot put 0 here, not defined. Okay, so what happens is that y double prime of 0 is not defined, so it is not equal to 0 because it is not defined, but still I have an inflection point there. But because this is not discussed in your book and your lesson, I will call this true at the level of your lesson. But this is not also true because this is a counterexample. Okay? But if you want to make it 100% correct, I will add one more sentence to it. Then it is always true, even if you go to university. So let me take this off. And because I want to write true, I have to be careful here. So when I say it is true, it means it is always true. And this is not always true, so let us make it always true. If is an inflection point, and if f double prime of a exists, this is the phrase that in the university you add to it, then it becomes 100% true. But in your book, because this is always guaranteed, you don't need to be worried about this phrase, so you say that, okay, this is true. Is the explanation clear? Okay, so if you really want to make it 100% true all the time, you have to add this extra sentence to it. Okay, why this is useful here? Because I have given they have given us a function, f of x is x to the third plus ax plus b, or ax squared. No, sorry, x to the 4, and this is 3. We are supposed to determine a and b in a way that -1, we are supposed to determine a and b in a way that -1 and 0 is function's inflection point. Okay? So, in principle, they are telling us that this function has an inflection point. You don't need to be worried about that, yes? So, this means that I, with the coordinates -1 and 0, is an inflection point. Inflection point. Okay, and on the other hand, you know something. You know that if you are supposed to find both A and B, you need 2 pieces of information because you have 2 unknowns. One piece of information is given to you. They are telling you this point is an inflection point. How can I use it directly? Yes?
You can write f double prime of -1.
No, before it, yes, that's correct. But before that one. Because when you say it is an inflection point, it is where? It is on the graph itself. Yes? So it means that before going to the derivative part, inflection point is a point on the graph. So it means that the coordinates of any point on the graph, including the inflection point, will satisfy the equation itself before even going to the derivative. So it means that from this equation, I immediately realize that f of -1 is 0. Or the y coordinate is 0, the x coordinate is -1, as you like. So I put 0 here, and instead of that one, I put -1. And then I get an equation, but with 2 unknowns. So -1 to power 4 is +4. I move it to the left, it becomes -1. Sorry, -1 to power 4 is +1. I move to the left. And then this one becomes -a plus b. So this is one equation. As the second equation is as Simon mentioned. Because which one I am using, do you think? Can you point it out? I am using this one or I am using this one. Because you see, I am not allowed to use this one because it is false. Be careful. But in this problem, I am not using this one because this is guaranteed to be an inflection point. And then I can conclude that f double prime of that point is 0. Why, by the way? Because this is always the case, because that's a polynomial. When it is a polynomial, its first derivative, its second derivative, any order derivative exists. So this means that I told you, this is automatically fulfilled. So you don't need to be worried about that. So this means that this is an inflection point, so this should be the case. So I would say that A, -1 and 0 is an inflection point. So this implies that f double prime at -1 is 0. And that is extra information that you need. So this motivates you. If I want to calculate f double prime of -1, I need to have f double prime. So this motivates me to calculate f double prime. But f double prime cannot be calculated unless I first calculate the first prime. So this becomes 4x to the power of 3 plus 3ax squared, and then that's it. And then I calculate the second derivative from it. So this becomes 12x squared plus 6ax. Yes? Okay, now I note the second derivative according to the problem and my own understanding. This is not given in the problem. You need to understand this sentence yourself. And then because of that, I realize that f double prime of -1 is 0. What does it mean? It means that if I go to f double prime, replace every x with -1, the answer is supposed to be 0. So let me just do that. I go in f double prime, I replace every x with -1, and then I know the answer is supposed to be 0. But this becomes 12, this becomes -6a equals to 0, so 6a is 12, so a is simply 2. When A is 2, I put it back in this equation. I will find B. So it's minus 1 is equal to minus 2 plus B. So B is 1. So you see the algebra is very simple. Okay? So, but this is considered to be a higher level problem in your book. And apparently it was right. I was expecting that you can solve it. So which part you couldn't?
I could. I just, for some reason, I wrote B minus 1 equals to 0, and my brain didn't realize that I had
Okay.
a solution.
Yeah, because I mean, it wasn't that hard. I mean, okay, anyway, this is a quite common question when you come to this. You see some of them in the book. Okay, and then I think it is a good idea to test this idea with GeoGebra as well. So let us go to GeoGebra. Okay, so delete all of these things. Okay, but my function, now I know what is A, I know what is B, I plug them back, I put them in this equation and ask GeoGebra to draw the graph of that function for those values of A and B. So A is 2, B is 1, okay? So y is equal to x to the 4th, and then I go down and then I have plus, what was A? A is 2, x to the power of 3, yes? And then plus B. Of course, B will shift it 1 unit up, yes? Well, that's the graph. And then, by the way, how many inflection points do you think this function has? Yes, it seems to be 2, yes? Because the concavity of the function is changing 2 times, yes? So for example, before this point, the concavity is up, and then you suddenly see that this part, the concavity is down, and then immediately after that, the concavity is up. So definitely it should has 2 inflection points, but it doesn't have anything against this problem. This problem tells you that minus 1 and 0 is an inflection point, which in this case is, yes, minus 1 and 0. This is an inflection point. But the function has also another inflection point, which coincidentally is also a terrace point, or it appears to be a terrace point. Okay? And by the way, let me see that if GeoGebra provides both of them for us this time, inflection point, and I type my function. If I learn how to copy paste, it will save my life, you know. X to the power of 4, and then plus 2, x to the power of 3, and then plus 1. Oh, yes, plus 1. Yes, so GeoGebra actually knows about both of them. It shows it on the graph, but let me see. Yes, the numbers are minus 1 and 0, and 0 and 1. So when it comes to polynomials, I think it is actually doing good. So what we did is correct. So we fine-tune A and B so that this point becomes an inflection point, and we check this using GeoGebra. We realize that yes, the numbers we found is completely correct because it worked. Okay, any questions? Okay, so this part is also finished. Before going to a very important topic of integrals, we have something more, and that's a little bit hard for students based on my experience, and that's optimization problems. So we had a little bit of this in Math 2C, if you remember, very shortly about the parabolas, but now we can do optimization problems for a variety of functions because we have a very strong tool in our hand, and that is the notion of derivative. Okay, so we will continue next week. Yes? Any questions? Okay, thank you.